All right. Good afternoon, class. Happy Tuesday. Hopefully you had a nice long weekend, or I'm not sure if you guys have any Friday sort of classes or whatnot, but I have a Friday and a Saturday class. So for me, it was a very nice long weekend. Anyway, so pretty much for right now, I'm just going to go over sort of first I'll outline kind of the semester in a nutshell that's going to be coming up. So this last month of our semester, we're going to have really not so much time left or not so many weeks left essentially. So I'm gonna go ahead and first outline this week. So we'll cover graph theory and greedy algorithms either today or on Thursday for greedy algorithm portion. And next week will be kind of interesting because next week, Tuesday, is going to be another faculty senate meeting that I have to attend. So what I'll do is I'm going to just make a pre-recorded video over the weekend and upload it up onto my YouTube channel. And then I guess that would be our Tuesday class. I don't want to really cancel because Tuesday is not really a holiday. So I guess that'll be our Tuesday class, just like we had the last two times I had a faculty senate meeting. I just had a pre-recorded video that day, and that was it. Next week, Thursday, is going to be Veterans Day, so we have to honor that day. So it's going to be another holiday. So no class on Thursday. So next week will be no real live class because Tuesday will be recorded. Thursday will just be an off day. The week after that will be our kind of final full week because the week after that will be Thanksgiving. So Thursday, again, we no class. After Thanksgiving is over, we have study week, if I'm not mistaken. So on study week, I mean, unless I really have to cover some new content, I plan on having Tuesday being our exam review, and then Thursday being just sort of a canceled class so you can prepare for exams for this class. For other classes, I always try to make the study week to be relatively not so dense of a week. So that way it's very light so you can prepare for your finals and so forth. So unless I have to cover something on study week, then of course I'd have a class then. But I really feel like that probably won't happen, but we'll see. So that's going to be kind of our semester outline. So you have a full week this week. Next week, sort of going to be a shorter week, then another full week. Then we'll have the Thanksgiving week. And after that, so we have really just this and then sort of not next week after we are two kind of full weeks left. So we're definitely getting towards the end. So it's kind of definitely nice when you get towards the end. Of course, it's always nice, winter time in Vegas. So of course we can't complain about that. So anyway, that's basically the outline of the last month or so of the semester. Let's go ahead and begin a screen share and sort of resume from last time's content. So let's start this. And there we are. So last time we covered DFS, traversal. So this was our code, our MIT's pseudocode from the book. So I wanted to kind of use the book example just so in case it was confusing, then you have the book as a reference to go through all this. But it's a very simple traversal depth first search. All we have to do is we have a start node. So you pick a node to start from, and all we have to do literally is just go to one, we just pick an edge, and we sort of go as far as possible we can in our graph. So once you hit a dead end, we back up to the previous node we came from and try a different path. That's really all depth first search really is. So just using that really weird code just to do depth first search. So we store these numbers, our sort of arrival time and our final time. So we arrived at node A at time 1, and time 16 is when we process node A. So these times tell us kind of the order in which we traverse nodes in our depth first search traversal. And then these pi sort of fields for every node is there to tell us the predecessor. So we arrived at node C from node B. We arrived at node F from node C. So the predecessor will tell us, so give us sort of which nodes are going to be in our, sort of which edges are going to be used in our DFS forest. It tells us sort of the order in which we traversed this graph. Using these predecessor pi values, we can very easily construct the actual paths that were taken by GFS on our graph. So this will be our GFS tree/forest. This kind of gives us the order, sort of the paths that we took to get from different nodes in our graph. So the blue and the red were back and forward edges, and in green, I guess that there was no cross edge. I can't think of a cross edge in this graph, essentially, or I guess maybe let's see, I think maybe H and G would be a cross edge. No, H goes to G, so never mind. So I guess I kind of created some, I fabricated some edge right here at the end, just to kind of show an example of a cross edge. But anyway, um, essentially have classification of edges, essentially when we go ahead and run depth first search on a graph. So basically, I guess the really relevant ones are really tree edges and back edges. The back edge really tells us if we have sort of a cycle in our graph. So let me go ahead and actually begin. I'm going to go ahead and just sort of go over a few more contents here with depth first search. So let's go ahead and just write a few more notes here. So basically, we can actually classify an edge. We can sort of mark an edge as one of these as we traverse traverse a graph using depth first search. So when we explore an edge U, V, the color of V sort of tells us the edge classification. Here's how we actually can tell what type of edge we have when traversing our graph. So if essentially, if V is a white vertex, then UV is a tree edge, which means that this is the first time we discovered this node V. So obviously this would be part of our GFS sort of tree edge. And then other classifications, if V is a gray vertex, then UV is a back edge. And also, back edge implies we have a cycle in our graph. I'll put this here as well. So a back edge implies a cycle in the graph. So basically, if a node is marked as a white node, that means we haven't discovered it yet. Gray implies it's currently in our DFS path. So it's a node that it's in our path essentially. So if you find an edge that goes to a gray node, then we found sort of an edge that goes back to sort of a node that's already in our path, which implies that means we have a back edge, and the back edge implies a cycle. And then, of course, the third classification as we traverse depth first search on our graph. So if V is a black vertex, then UV is a forward or a cross edge. So at this point, you really can't tell which one it is, but you can use the predecessors of U or V to verify if U or V is sort of an ancestor, is that the right word, ancestor of let's say, if you use the predecessors list, you can verify if either one of these is an ancestor of the other, and then you can tell if it would be a forward edge or a cross edge. So you have to have a loop that would go through and goes through the ancestors with that pi list. So, each node has that predecessor, so pi, so a dot pi, b dot pi. So we use that to verify if it's a forward edge, if either U or V is ancestor of the other. So that's how we can actually verify this. Now, for runtime of depth first search, it's pretty simple. I think you might have learned this in 302. It's going to be O of E plus V. So remember, this is set theory, so it's going to be the cardinality of V and the cardinality of V. So basically, I know they use this for some reason, O of E plus V, but really it's O of E essentially. Depends on how many edges you have in your graph. So I guess it's O of V if it's a sparse graph, and it's O of V if it's a dense graph. But either way, E, that set could be V or V squared. So really, the number of edges you have in your graph really is going to tell you the runtime for depth first search. So that's that. So, of course, I could modify this code a little bit. So how do we actually write depth first search to actually cycle exists? Well, basically, if a back edge is found. So if you go up to our code, um, if let's say if v.color equals gray, cycle is found. So you can actually have your statement right there that checks for that. So I'm not going to go over the example of how to find a cycle in the graph. That's kind of a 302-ish thing, but also would not be very hard to actually write. You just take that code and add the if statement in there to be able to determine if a cycle exists. So I'm going to cover another topic over here, which I might use later in the semester again if I get far enough in this course. So we'll see how far I get with material. I want to cover topological um, sort, sorting of graph, which this can be used actually for shortest path algorithms, but we'll see, how far we get on it. But I think I might have enough material. I have 6 more lectures or so, so I can probably get through that because I'm going to try to cover that at least, but we'll see how far we get. But anyway, let's go ahead and talk about topological sort right here. So basically, it's sort of, well, for one, it only works on directed acyclic graph, known as a DAG, yes, which is the abbreviation of that. So basically, it's an ordering of nodes um, that sort of, I guess you could say that respects the dependencies of the graph. So the best way of thinking about this, I'm going to use the following example. So I guess we can think of sort of, we can have it actually where we can have a graph where each node is a CS course number. So it'll be kind of the example I'll use. And an edge denotes a prerequisite. So since we are kind of on that topic of registration for courses, that's kind of been everyone's mind is sort of on that right now. So I guess we can go ahead and use that as an example. So basically, each edge is a dependency. So an edge from A to B means you have to have first been at node A before you can go to node B. That's sort of the idea with this. So a topological ordering, in this case, would just basically just tell us sort of the proper list of courses you can take, which respect this dependency or this respect the prerequisites of this graph. So basically, what we're going to do to run topological sorting. So I guess the go over like sort of the sort of pseudocode for this algorithm. Basically, what we're going to do is you're going to run DFS on the graph, and what you do is so when a dead end is reached, which is when you do DFS, remember at some point we hit a dead end. Either we hit a node that has no neighbors that are unvisited, or we have a case where there's no neighbors at all, so then we're done. We hit when dead end's reached, we're going to push the node, sort of the node ID onto a stack. So before we return out of a DFS function call, we first push that node onto the stack and return. And at the end, the stack from top, bottom contains the topological ordering. So at least from what I've seen, this is mostly used, at least for practical application, is for shortest paths. So if you have a directed acyclic graph, you can compute a shorter path in faster time than using the standard shortest path algorithms. So that's why I'm saying we might get to that point in this class. We'll see how far I get. So this is kind of where we actually have a good example of where a topological ordering is going to work. But I'll go ahead and I'll use an example that could be more relatable to this, I guess, to present times right now. So let's go ahead and create a graph. So I'm going to label these as just 135, so as numbers. So 135 is that first course you take. Then we have, I guess, 202. Then we have, I think, 302 and 218 would come after. These are kind of after 202, I believe. Then we have 219. Then we have 370. I'm going to zoom out of this a little bit because I'm running out of space here. 370. See what we have next. Then I think we have 477, which I'll put this 370 down here. I guess then 477 comes next. Let me move this down once more. I think we have, what's that one class? 456, I believe. Talmud theory class. Then we have 460. Yeah, I think I'm gonna go with that. I think that works. So here's gonna be our set of courses. I'm going to just circle these in. These will be our nodes in our graph. I think I got most of these, although I'm not really sure what the prereqs are anymore. They always change them every single semester, it feels like, so I don't know what the prereqs are, but I'll go with that as our prereqs. So I'm going to basically just draw the following lines. I didn't create a straight line out of this. Try over time. Doesn't do it then, so well. Oh well. I want to make it work. Connected those. And let's see, we have this. Then we have 302 has several. I think all these, all prereqs, I think. I mean, I'm not going to consider math classes, just consider CS only. And then we'll have 302 also goes over here, 370, 219 for that as well. And then 460s, compilers, I believe. Yeah, we'll go with that. So here's going to be our graph. I'll draw the lines over here. So it's going to be directed acyclic graph. So we see that we have this graph, and there's definitely no cycles in this graph. So you can't have topological ordering if you have an acyclic or if you have a cycle in your graph, which I'll show in a second why that's not going to work. But it's going to be our set of nodes, and it's going to be our course numbers, and these arrows are going to be prereqs. So you have to first take 302 in order to take automata theory, algorithms, and I guess operating systems. And I think that's going to be, I think that's good enough. I think that's sort of how we have the prereqs for our different classes. So basically, to construct topological ordering, so an ordering is going to be just a list of these nodes that maintains this. Well, it's for well, okay, so where's 472 going to be with respect to all this? I'm going to say 370 is a prereq, but I'm going to say 370. Actually, pretty important class 472. It's your senior design class, so that's always important. 326 as well, yeah. Forgot about Ben's class, actually. I guess I could just say, let's forget about it. So I think it's, let's take a look here. Let's see what's the comments here. 326. Okay, I'm going to go ahead and I guess 326 is prereq. Let me see. I'm going to first just have 370 for right now. Let's see. 326, I think it needs 302, I believe, right? And see what else you need for 326. Maybe 219. I think for now, just keep it like this. So I'm going to go ahead and disregard 326 just to kind of mess with my. Oh, okay, it's 19. So, okay, it's 19 and 302 is for 326. Okay, perfect. So I'll put 326 over there. So if I'm not going to troll my friend Ben, 326, a fantastic instructor actually, but I'm going to, of course, every now and then just kind of mess with him just because. So we need to have these two. And these two are needed. 77. Yeah, I think we got a pretty nice graph going on. It's pretty complicated, so it definitely works as a graph. Okay, so here we go. So of course, we don't have any cycles in this graph, so we want to go ahead and list out the courses that are takeable, that are in that order. So for example, we can't take 302 before having 202. We can't take automata before 302. So we have these edges which will represent these prereqs or dependencies in a graph. So the way we actually construct topological sort is you first just run DFS. So right now, I'm going to mark all these as, I guess, as white, so which means that these nodes are not been looked at yet. Then blue will represent gray and red will be black, so it's going to be how we're going to mark them as processed. And I'll go ahead and I'll put a stack the bottom over here. I guess, yeah, I guess I can do it kind of from right to left. This stack will be tilted on its side, I guess. So I'm going to kind of construct the shape like this. Maybe I can't. I think I can do this. So I'm going to have a stack that's going to be sideways on its back, basically. Let's go ahead and do that. And we'll go ahead and work this out. There we go. So the first we do is we go ahead and run DFS. We start from our first node, 135, and then we're going to mark it as gray. It only has one neighbor, so we go to this node right here. So the 202. So I guess I could even mark them with times actually. So I'll go ahead and I'll just put one over here. So I'm not going to actually use discovery and file. I'm just going to use just discovery times for now. So I'm going to just put one here and then two for this one, so you can see the order in which we traverse this graph. And then for 202, so we have sort of this, how shall we say, two different possible paths. So I'm going to choose 302, the next one. It's going to be the third element to be visited. Now from 302, well, let's see. Maybe we can get 477 done the way earlier. So we jump to this node next, mark that as gray. And then we're going to basically at this node right there, we hit a dead end. Because from 477, I think there's no classes that come after this one. So at this point, we're going to go ahead and push 477 onto our stack. And we're going to mark this as now going to be red. It means we process this node. So we go back to the previous element in our previous node in our graph using our simple depth first search traversal. We jump back, and maybe I'll go ahead and maybe I'll put 5. Maybe I'll go ahead and I'll do it like the right way, just to kind of make things easier. So then we go back to the previous node. We have 3. We go back to 302, and we're going to choose this time maybe 326. So this will be time 4. We're going to mark this as gray. And then from 326, we really can't go anywhere else other than the 477. So, oops, it should have been 6, my mistake. 6. So then what happens is we're going to now jump over here, mark this as 7. And now we see here, well, from 472, we can't go anywhere else. So we're going to push 472 onto our sideways stack. And we're going to mark this as processed, and then the destination or the final time will be 8. So we finish this at time 8. Sure. Then we go back to 326. We go back a level, and 326, well, there's no other neighbor anymore. So we're done with 326. We hit a dead end, if you will. So I'm going to mark this red. Destination time is going to be 9. And we're going to push 326 onto our stack. So once we hit a dead end, or once we're done with this, then once we mark this node as red, as done, then we're going to push it onto our stack. Okay, so now we have to go back to the previous elements. So 302 was where we last left off. So I'm going to go ahead and choose automata theory this time, just because. So then I'm going to go to this node, mark it as blue, and we visited this at time 10. And then we're going to see, well, we have one neighbor for 456, which would be 460. So we jump to that element, mark this as gray, and time 11 is when we discovered it. Then we see here, well, we have nowhere else we can go. So we hit a dead end. So time 12 is when we sort of marked it as processed. And we're going to insert this into our stack, put 460 right there. We go back to our previous sort of elements. So we go back to 456 now. And we see here, well, we process as one neighbor. So now we're done with this node. So we're going to mark its final time to be 13. Mark it as red. And we're going to push this onto our stack. 456. Now we go back to the previous node. We go back to, I guess, 302. Because that's the node we came from. We processed 456. So for 302, we tried several different paths. We have not tried 370 yet. Let's go ahead and look at the other neighbor, which will be 370. Which at time 14, we're going to visit 370. For 370, well, we have nowhere to go. We have one neighbor, 472, but we already processed 472. So we have nowhere to go. So we're going to mark the process time, mark it red, and we're going to push 370 to our stack. Return back to 302. So for 302, looks like we processed every neighbor. So 302 is officially going to be done. So now we can go ahead and mark it as processed. Its final time is going to be 16, and we're going to push 302 to our stack. Then we go back to the previous node, which was in fact going to be 202. So from 202, we tried one neighbor, 302. The other neighbor is going to be 218. So we're going to try 218 next, mark it as gray, and the number we're going to associate will be 17. That's going to be in the time stamp that we visited 218. And then from 218, well, we only have one neighbor, 219. So let's go ahead and jump to 219 next. Mark it as gray, and its discovery time will be 18. Looking at 219, well, we have two neighbors, 326 and 370. So basically, we've already processed both of them, so we can't go anywhere else. So we're done with this node. So we're going to mark it with the destination or final time, mark it as red, and push 219 onto our system stack. Return back to the previous node, which was 218. We came from 218, and from 218, well, we processed this one neighbor, so now we're officially done. So now at time 20, the 20 timestamp is when we're going to have this node finished. Push 218 onto our stack. go back to our previous node, which was 202. That's where we came from. And we process both neighbors. So now we can officially process this node as well. Time 21. Push 202 onto our stack. Turn back to the previous node, which was 135, which where it all began basically. And at time 22, we can say we're done because it has no other neighbors to process. We mark it as processed, 22, and then push 135 onto the stack. I guess I can try to extend this a little bit. Good enough. Extend this one as well. It's going to be our sideways stack. I'll try to do a little nicer. So that's our sideways stack. So our rightmost element is going to be our stack top. I guess I can't get this to be straight, but you know what? That's fine. It's still visible. So anyway, we can try to move this. We can try to circle this and try and see if I can actually move this if I can. It's okay. So that's going to be our stack basically. So now from our stack top, we can go ahead and just, do a pop output when it pops and keep doing a pop operation one by one. So then our topological sort would basically just be first you pop 135 and output it. I'll put sort of a green arrow just to kind of denote that we popped it. So you still can see it. Then we pop it again. I'll put 202. Then I'll put 218. I'll put 219. I'll put 302. I'll put 370. I'll put 456. Put 460. Pop this off. Then 326. It's kind of odd how you in this kind of order, but I guess this does work. This order does work. I guess it does follow the prerequisites. Then 472. And at the end, 477. Then our stack is empty, and we're done. We have our stack, and we just sort of one by one, we pop it on and off, and we output it, and that's going to be our topological sort. Now, of course, there's more than one possible way to get topological ordering, but this is just one valid way. So depending on if let's say you have many different choices you can take, so like in this graph over here, I'm try to zoom out so we can see all of this. So we have different possible choices, and choices do make life a little bit challenging because then what order do you take them? Well, here is one ordering. So I guess, your advisor you talk to before you register for classes, they can just go ahead and run this program and randomly pick different edges and give you your topological sort. This is going to be your graduation plan. So you could use this approach to do that, which I don't know if it's going to be the best idea. It's not really tailor-made for each person, but I guess this is just one of many different possible topological sorts. So basically, that's all you have to do. So you just go ahead and call DFS, and before you backtrack, you push onto the stack. Then the stack top to the bottom is going to maintain your topological ordering. And this is going to preserve the dependencies of your graph. So each edge is a dependency. So we can see here that 302 and 218 can be taken at any time, but they both have to be, you first have to have 202 first. So we can see here, the bottleneck is 135 and then 202. After that, then we have a little bit of choices. Once you have 302 done, you have a lot of choices after 302. So it's probably that's why students take 302 right away, because then a lot of choices pop up, which will definitely help them along the way. So we have a lot of choices. That means there's many different possible topological ordering. So there's more than one, obviously, for a graph, especially if a graph has different choices like this. So that's going to be an example of topological ordering. So nothing really too bad there. So of course, if you were to run DFS, let's say if I would have chosen 218 before 302, then we'd have a different possible topological ordering. So just know there's more than one possible topological sort for a graph. It depends solely on which edge is chosen by DFS when you run DFS on a graph. So anyway, now let's go over the fact that this only can work on a graph with no cycles. So this example right here, we see there's no cycles in this graph. So let's go ahead and do another sort of real world example as to why it will not work if you have cycles in your graph. Let's go ahead and zoom in on these notes so I can write some stuff out. Let's write like this. So a topological sort um, does not exist if a cycle is present in graph. So, I mean, the way we can sort of show this, let's go ahead and show the vicious cycle right now. Okay, so I guess let's go ahead and do this. We have school, then we have, let's see, then we have an internship, or about school and job experience. This is going to be fun. Then we have, I guess, a job, an actual job. And let's go ahead and do this. Let's suppose we have a cycle. And I don't know if experience, but you know, some students, some people have experienced this vicious cycle. This came out wrong. That's okay though. So consider this cycle. So in this example, well, the problem is what's your starting position? So you have to have school in order to have job experience. You have to have job experience to have a job, but then in order, I don't know, this makes actually, it's not a very good example. But anyway, this makes no sense at all, which actually that's good because it shouldn't make any sense because you can't create a topological sort here because you have to have school in order to have job experience to have a job, but in order to go to school, you have to have a job first, which is like, well, that does not make sense because that's impossible to actually pull this off. So you have this situation, there's no ordering. You don't have a starting point because each of these depend on one another. So when a cycle is present, each node depends on one another. So there is no starting point. I think maybe it should have been better. I think it's like job experience and I know it's like the vicious cycle that we all kind of know and love. So anyway, in this example, there's no starting point. You can't begin anywhere because you can't start with a job because you got to have a job experience first. In order to have that, you can see here that it's not going to work basically. So you can't really have a cycle in the graph and expect to have a topological sort. So you only can apply topological sort on a graph that has no cycles. But of course, if you're given a graph, you can very quickly determine if a cycle is present. You can use DFS one time just to check and try to find any back edges. If you can't find a back edge, then you know there's no cycle, so now you can go ahead and run DFS again to actually construct sort of a topological ordering. So obviously the runtime for this, runtime for topological sort, is, well, just like with DFS, it's O of E plus B, same as depth first search. Now, if the graph you're given, if you don't know if it's acyclic, you can of course run DFS once to see if any back edges are present, and then run DFS again to basically see if there's, then run DFS again to actually construct your topological ordering. So in the worst case, you do two runs of DFS, which is not going to hurt the runtime. It will still be O of V plus V. So kind of a simple example, topological sort. So I guess I could have a homework assignment at some point, maybe next week, and just depth first search, topological sort, nothing really too bad, just a little time consuming, but definitely shouldn't be anything really, shouldn't cause any panic to get that homework assignment. So now let's go over one last example that involves depth first search for some problem. So it's going to be for the following topic. So let's go ahead and put a line here to separate this. Let's go over the following. So strongly connected graphs, or we can also think of it as strongly connected components. So actually, I'll just not have it loaded in its own kind of heading, I guess, here. So basically, a strongly connected graph or component. So a strongly, so I'll put a bullet. A strongly connected component is a component or I guess it's either going to be either a graph, sorry, so it's going to be either a complete graph or subgraph where each node is reachable from any node in the graph or subgraph. So sometimes, for different graph applications, it's good to know which components where these nodes can all be reached among themselves. So it's good to have that sometimes. So for certain applications, you may want to have that. So anyway, let's go over the algorithm for how we actually do this. So it's again going to rely on DFS. So DFS is a very nice traversal for graph. It's a very simple traversal to follow, and also you can do all kinds of interesting things with graphs. So it's a very nice traversal to use. So DFS is just mostly used to do different problems like topological sorting, for strong connected component in the graph, to find a cycle in the graphs, all kinds of uses for depth first traversal. Let's go ahead now and go over this algorithm. So let's go ahead and use DFS to work out this strongly connected sort of graphs or components. So let's go ahead and write this. So we'll have our pseudocode right here. So basically, there's not much really to this, but I'll do an example, of course. So we got to first call DFS to compute, I guess, these u.f times. It's going to be that final processing time. So those numbers in red in the earlier example. We're going to first compute those. Then we're going to transpose the graph, which really just means that we're going to sort of going to reverse the edge direction for each in graph. So that's all transposing does. And then third step is we're going to go ahead now call DFS on this transposed graph. And we're always going to start, so we're going to start with nodes that have the largest graph times. So this could become a graph we have to call DFS more than once, possibly. So we first call DFS on a transposed graph on the node with the largest final processing time. Then we go ahead and call DFS, and we output sort of the nodes in a DFS traverse. That's going to be a strongly connected component. So basically, just sort of, output nodes. And then this is going to be this is going to be a strongly connected component. So the idea is that, so in the book they use this, they say pick the largest sort of final time. What you actually could really do is once you've processed a node, you push it onto the stack and use the stack as the next node to be processed. But I guess I'll go with what's in the book just to be kind of safe. So let's go ahead and just construct a graph with this. So there's not much really to look at here with this pseudocode. We just use DFS twice and that's it. So we already can see the runtime will be O of E, basically. But I'll write that runtime down at the end. I put the runtime down for topological sort. I did, okay, perfect. So I did that. Let's go ahead now and just create a graph and let's run this this algorithm on this graph and see if we can figure it out, see if this algorithm actually will work. So I'm going to just first create a couple of nodes first and foremost. So let's have maybe this. I'll have this, that, and I'll have, yeah, let's go with that. Let's see if I can see an example here. Okay, I'll go ahead and I'll just maybe this. Just put this over here. Okay, I think it's a good enough example. So over here, this is going to be its own little cycle right there. Yeah, probably should have, let's see, I'll put this here like that. Put these over here, and I guess I'll have it like. Okay, I'll label these, so A, I guess I could make it like a little CA. Confuse it with I. So we can kind of see here, if I didn't mess up this example, we can see in this graph, this is going to be one strong component. This will be our other. This will be our other one right there. Then this is going to be its own by itself. So basically, within A, B, C, and D, we can reach all of these nodes in that component. And if you jump to this node, so we go to node E, E and G are back and forth, but we can't get back to anything else. So that's going to be its own little component right there. H, I, and J will be its own strong component as well, and F is all by itself. So that's going to be sort of the solution. We have to, of course, figure this out using the algorithm, but we can sort of look at it right there. That's sort of the solution to this problem. Let's go ahead and see how this algorithm we're going to traverse is going to actually compute this result. So I'm going to remove all of these. Let's begin. So first thing we'll go ahead is we'll first run DFS just on this graph over here. I'm going to first copy and paste this. I'm going to have to transpose this in a second. So I'm going to first copy and paste it before I do anything else. Actually, not yet. I think I'm going to go ahead and copy and paste it with the numbers actually intact. Never mind. So right now, all these are going to be marked as unvisited. This. I'm not going to really maintain the predecessor pi, just mostly maintain the starting and ending times. We first will start with A. Sure, I'll start with A first, I guess. So then what's going to happen is we're going to mark this as sort of gray, and then we're going to have our number 1. That's in the first, we first visited A for the first time. So now let's go ahead and run DFS. So I'm going to now, I guess, only one edge I can choose, which will be just B. Mark this as gray. And then from, I guess, at this point, I'm going to go ahead and just make this simple. I could choose E or D if I wanted to. I'm going to choose D just to make this a little bit easier. Either way, it will still come out the same way, though. So I'm going to go ahead now and choose this edge. That's 3. Then from D, I'm going to pick C with the timestamp 4. And C has nowhere to go because C can go to A, but A is not marked as unvisited. It has a blue marker on it. So we're done with this. We're going to go ahead and set it to 5 as destination time. Mark it as processed. Go back to the previous nodes. We have D. And then from D, we could try F next. So we're going to go ahead and mark this as part of our DFS. And I'm going to use time 6. Then from F, well, we could go to E. That's only where we can go, actually. So we're going to mark E as now blue, put 7. And then E can go to G. So G has, so G is not visited, so we mark it blue, put 8 over there. And then from G, I'm going to now try the next sort of path, next edge, which will be, I guess I could try E, but E is already marked as blue, so I can't do that. I'll try H. Mark this as visited. It's a 9. And H can only go to J, so J will be marked as visited. 10. And J can go only to I, so mark this as visited. And 11. And I has nowhere to go. So what's going to happen now is we're going to mark it as processed. Go back to the previous node, oops. Go back to the previous node J, and J has nowhere else to go. So mark it as processed. 13. Go back, so from where J came from H. So we're going to now go ahead and mark H as processed. That. Go back to the previous node, so G. G was actually the last, so sort of the predecessor of H, and G has nowhere else to go, so mark it as processed. 15. And then go back to its predecessor, so it looks like it was E. E has nowhere else to go, so mark it as processed. 16. Go back to the predecessor, which was F. F has nowhere else to go, so mark it as processed. 17. So let's go back to the the previous element, which was actually D. is where we came from, and D has nowhere else to go. So, oh, okay, never mind, there it is. Has 18, and go mark it as processed. Go back to the previous neighbor, which was predecessor, which was B. B has nowhere else to go, so mark it as processed. 19. Go back to the previous element, which was A. A has nowhere else to go, mark it processed. And 20. So here's going to be our DFS. We have our discovery times and our final times for every single node. So now taking this graph, I'm going to copy this graph actually, and then modify the edges. So I'm going to go ahead and copy this one first, just right over here. This is the so DFS results on initial. We can see right there in front of us. So now I'm going to go ahead and transpose this graph. So I'm going to go ahead and sort of copy this graph right here, or sorry, paste it right here. So it came out decent, so it didn't mess up too bad. Let's go ahead and transpose this graph. So transpose is pretty simple. All you have to do is just reverse every edge. So I'm going to go ahead and put it like this. I should probably mark it with different colors so I don't make a mistake. So I'm going to go ahead and mark it as green. There we go. It's going to reverse this. This. That. Just both of these. So let's try to reverse this one. So we won't go like that. And like that. So it looks like everything was actually just, everything is fine. So it looks like it's going to be our transpose graph. So I'll put this over here. Our transpose graph. I took the graph and I just sort of just reversed all of the edges, all the arrows. I just sort of swapped them. So instead of A going to B, now B goes to A. That's all we did. So very simple to transpose a graph. If you wrote the code for this, it'd be very simple to do this. So now we have our transpose graph. Now we're going to run DFS on this transpose graph. So I'm going to right now see if I can, how do I actually make these nodes look nice? I think I'm going to go ahead and use green over here on these dots. So we just want to mostly have to make sure we know what was the last node that was sort of processed. So a stack could be used as well, but I'll use this method that was in the book. So you first have to look at 20 as our biggest processed number. Starting from 20, we can output our components. So our first, so we have a strong component. So our first strongly connected components, all you have to do is just output them in DFS order. So you first output A. I'll zoom out so you can see this. So you output A first. Then we have C. I'll put C next. Then after that, we output, we go to node D next. Output D. Then we jump up to B. Output B. And we hit a dead end. And then from D or C or A, we have nowhere else to go. So we're going to have to restart DFS. So if a restart means we're going to go ahead and construct a different strongly connected component. So the first one was, let's say if this whole graph was one strong component, then we would go ahead and sort of run through all the nodes on this transpose graph right away. But since we have a case where we start from A, C to D, and then D goes to B. We have nowhere else to really go after that. Then we have to return back to A. So we basically finished our first forest, if you will, of our DFS on our transpose graph. So that's going to be our first component. Now we have to go ahead and restart DFS again because we have not actually went through we didn't go through all the nodes in this graph. So you have to go ahead looking at all the nodes that are not marked. In this case, put that green marker on each node that we've already processed. So right now, out of all of our nodes that we've actually processed, the one with the biggest destination time will be F with 17. So from F, well, where can we go? Well, we can go to D, but it's already been processed, so nowhere we can go there. So in this case, we output the F, but then nowhere else we can go. So that's it, basically. That's the end of that DFS traversal. So again, well, we're not quite done because we don't have all the other nodes looked at just yet. So you have to continue with this process. So then third, strongly connected ones. Every time we have to restart DFS, we have another strongly connected component. So over here, looking at this, out of all of our nodes that are not been processed yet, looks like E with the value 16 is the biggest final time that's not been processed. So let's go ahead and looking at E, we're going to go ahead and run DFS. So first, go ahead and output E. That's going to be the first node in our traversal. We'll mark it as processed or visited, if you will. And then we go to its neighbor. So it can go to B, but B's in process, so we don't go there. G has not been processed. Let's go to G and output G right away. As soon as we arrive there, we're going to output G immediately. We'll mark it as visited. And then from G, we have nowhere to go in this transpose graph. So that's another component we discovered. Another strongly connected component with E and G by itself. So looks like it is actually working so far. Let's continue. So right now, we still have some nodes that have not been processed yet in our graph. So out of those, the biggest final time is going to be 14 for H. So it's going to be our fourth strongly connected component. So we're going to first output H and mark it as visited. The next element in this transpose graph, I guess we can go to I. So we're going to go to I and output I. Mark it as visited. Go to next, so from I, we can go to J. Simply output J. It will mark it as visited. And J has nowhere else to go because J can go to H, but H has already been marked visited, so that's it. And now when we return out, every node has been sort of processed. So we have our four components. So I'm going to put this in sort of set notation. Is our first component, second, third, fourth. And of course, I can go ahead and sort of circle these. So it's going to be our first component. These nodes basically. Then we have these two. This is our third component, sorry. Our second one we constructed was this one. Then our third is that one. So first, second, third, fourth. So that's how we can actually find strongly connected components in a graph. That's basically how we do it. So we have to run DFS twice, and we transpose the graph first. So when we output, we can, of course, we can output them, or we can push it onto a vector or something to push all the nodes that belong to a component. And once we have to restart DFS, that's going to be a different component, different strongly connected component. And we can see here in this graph, each component, each node, by looking at A, so if I go back to the original graph here, so A can go to B, B goes to D, D goes to C. So each of these nodes can be reached from any of these nodes. Same thing for E and G. If I'm at E or G, I can reach the other one. In this component, I can reach H, I, or J from any of these nodes. But from F, I can only reach itself. I can reach E, but E can't go back to F. So E and F would not be in its own component because F can go somewhere, but then there's no way to get back to F, essentially. So that's basically it. So let's go ahead and do the runtime analysis of this, and I think then we can probably call it a day. Let's go ahead and just, what's wrong with OneNote? OneNote's been acting weird on me today. Okay, if I'm gonna go ahead and close this and reopen OneNote. I have to restart I have to reinstall Windows maybe, I'm not sure. It's really been acting up on me today, so. Okay, let's go runtime analysis, and then we can go ahead and call it a day. All right, perfect. So, runtime analysis for strongly connected algorithm, whatever it's called. I'm going to call it that. So the first step is you do DFS on initial graph. Well, I mean, that runtime is going to really just be O of, I can use different, I use red to do this. It's going to be just simply O of E plus V. I mean, that's really the runtime for DFS. So that's no difference here, just that. So that's going to be the runtime for the first DFS. And then to transpose the graph. So if you're using sort of adjacency matrix, you just have to basically just swap them basically. And so actually all you have to do is take your matrix and just kind of just shift it like that, which is going to be a nested sort of for loop. You're going to go through E steps, number of edges, number of steps. If you have adjacency matrix sort of list, I'm sorry, then all you have to do is just go through each neighbor in that linked list and then just basically sort of push it into the, so you create another sort of adjacency list basically, and you just sort of take that element, go to that index and push sort of the the source node on there. So I guess I want to go through all that, but the idea is though, is it'll take O of E time is the idea. I want to go through all the steps. I don't have too much time, but it's a very simple process to transpose a graph. If you have the matrix or the linked list version, they both will take O of E time. And then to run DFS on transposed graph, well, that also takes O of, I guess, E plus V. I suppose I could also do plus E plus V on this one as well, because once again, it could be a sparse graph, it could be dense graph, so same idea. So we do three main sort of operations, and each of these takes O of E plus V time, and we do it at most, not at most, we do it exactly 3 times. So we're doing O of E plus V plus O of E plus V plus O of E plus V. The overall runtime is O of E plus V. Pretty nifty. It's a pretty elegant algorithm. It's pretty fast. It's linear with respect to the edges. So if you have E edges, it'll take E steps. So it's very nice. It's a nice linear algorithm on your graph, basically. So that's basically it for today. So next time we'll go over breadth first search. which is another type of graph traversal. And then we'll go over probably greedy algorithms for the first time. We'll cover a greedy algorithm on Thursday, and we'll see how far we get. So I guess for right now, take care, you guys. Stay safe. Thanks for watching. Have an awesome day, and I'll see you guys on Thursday.